Welcome to The Explainer. Okay, let's just dive right in, because today we're taking a seriously mind-bending journey into the universe's most extreme laboratories. We're going to explore a place where the foundational rules of our reality, gravity, and quantum mechanics are forced into a violent, direct confrontation. We are, of course, talking about black holes.
It's literally the fundamental question that has puzzled and fascinated scientists ever since Albert Einstein first published his theory of general relativity way back in 1915. For a long time, the math predicted these things, but they honestly seemed too strange to actually exist. So what exactly is a black hole, and how does it actually function out there in the dark?
All right, first things first, we've got to completely bust the biggest misconception out there. A black hole is not some ravenous cosmic vacuum cleaner that violently reaches out and sucks up everything in the galaxy. That is pure Hollywood fiction. In reality, a black hole is just an incredibly dense concentration of matter with immense gravity. Think about it this way. If you were to magically replace our sun right now with a black hole of the exact same mass, the Earth wouldn't get sucked in. Our planet would just continue orbiting it normally. I mean, we'd freeze to death in the dark for sure, but our orbit wouldn't change at all. To really grasp how these bizarre objects work, here's our roadmap for today. We're going to cover 1. Birth of a monster, 2. Anatomy of the abyss, 3. The spaghettification experience, 4. Monsters of all sizes, and finally, 5. How black holes die. So let's get started. Section 1. Birth of a monster. It all kicks off with the violent, explosive life cycle of a massive star. You see, a star is essentially this incredibly delicate balancing act. You have immense gravity pulling matter inward, and the nuclear fusion in the core pushing energy outward. But eventually, a massive star, we're talking one that is many times heavier than our own sun, runs out of that nuclear fuel. The balance is suddenly broken. In literally a fraction of a second, gravity wins. It crushes the core inward with unimaginable force, while the outer layers of the star get blown away in a massive supernova explosion. If that collapsing core is heavy enough, it just keeps collapsing, squishing all that mass down until its gravity becomes so insanely strong that a black hole is born. Moving right along to Section 2, Anatomy of the Abyss. Okay, so the absolute crucial point here is the event horizon. Because black holes pack so much mass into such a tiny space, the gravity right around them is completely unfathomable. The event horizon is the boundary around a black hole where the escape velocity becomes faster than the speed of light. And since nothing in the universe can travel faster than light, well, nothing can escape. The legendary physicist Stephen Hawking actually compared this to a canoe going over Niagara Falls. If you're above the falls, you can paddle away if you're fast enough. But once you cross that edge, you are lost forever. No light, no matter, no radio signal can ever paddle fast enough to come back. And if you do fall past that horizon, you are headed straight for the singularity. This is a region of infinite density in zero volume, where the fabric of space and time literally breaks down. But here's the truly mind-bending part. The singularity isn't really a physical place at the center of the black hole, the way the iron core is at the center of the Earth. Because space and time become so radically warped inside the event horizon, their roles actually swap. Moving toward the center literally means moving into the future. The singularity is an inescapable event residing in the future of anything that crosses that horizon. You can no more avoid the singularity than you can avoid tomorrow. But here's a wild twist. Despite their chaotic, completely mind-bending interiors, black holes look remarkably basic from the outside. In physics, this is known as the no-hair theorem. It states that an observer on the outside can only ever measure 3 properties of a black hole: its mass, its spin, and its electric charge. That is it. Whether a black hole is made out of collapsed stars, antimatter, or, I don't know, a billion tons of bananas, all that unique information is completely lost to the outside world. It becomes an incredibly simple object, almost like a giant elementary particle. But I know exactly what you're wondering. Section 3, the spaghettification experience. Because extreme gravity warps time, what happens when you fall in depends entirely on who is watching. Imagine you're fallen in and your friend is watching from a safe distance in a spaceship. To your friend, you would actually never cross the event horizon. As you get closer, the intense gravity causes your time to pass slower relative to them. They'd see you slow down to a crawl, seemingly freeze right at the edge, turn dimmer and redder as your light loses energy struggling against gravity, and eventually you just fade away. But from your perspective, you'd fall right through totally normally. You wouldn't notice your own time slowing down at all. Instead, as you look back out, you'd see the entire rest of the universe playing an incredibly fast forward. But your normal journey wouldn't last very long thanks to a very real and admittedly slightly humorous-sounding scientific term, spaghettification. Because the mass of a black hole is so tightly concentrated, gravity gets intensely stronger with literally every inch you move closer. If you fall in feet first, the gravitational pull on your feet would be millions of times stronger than the pull on your head. This massive difference in gravity would stretch your body violently in a vertical direction and squeeze you in a horizontal direction until you're pulled into a long, thin string of atoms resembling a piece of spaghetti. So, yeah, definitely best we keep our distance. Section 4. Monsters of all sizes. Black holes are scattered all across the cosmos, and they generally fall into a couple of main categories. You have your stellar mass black holes, which are born from dying stars. These are usually anywhere from 3 to 100 times the mass of our sun. The closest one we know of to Earth, Gaia BH1, is a stellar mass black hole about 1,500 light-years away. But then you have the true titans, supermassive black holes. These lurk at the very center of nearly every large galaxy, including our own Milky Way. They can be millions or even billions of times the mass of our sun. The largest one ever observed, TON 618, is an absolutely staggering 66 billion times the mass of our sun. Just let that scale sink in for a second. But they don't last forever. Section 5. How black holes die. For decades, scientists just assumed a black hole could only grow. But back in 1974, Stephen Hawking used quantum mechanics to prove they can actually shrink, revealing this brilliant, completely counterintuitive twist. In the vacuum of space, pairs of virtual particles are constantly popping into existence and immediately destroying each other. But if this happens precisely on the edge of the event horizon, one particle can get sucked into the black hole while the other escapes into space. To conserve the energy of the universe, the black hole effectively pays the energy debt for that escaped particle. Slowly, particle by escaped particle, the black hole radiates its mass away, a process known as Hawking radiation, until it ultimately evaporates in a massive explosion. But look, do not wait up for this to happen. This evaporation process is excruciatingly slow. The larger the black hole, the colder it is, and the slower it evaporates. For a supermassive black hole, the timeline is almost incomprehensible. But even for a microscopic, hypothetical black hole the size of a tiny speck of dust, it would still take roughly 10 to the 44th power years to disappear entirely. That is 10 billion trillion times the current age of our entire universe. So the crucial point to take away here is this. Black holes do slowly delete themselves from the universe. And this brings us right back to physicist John Archibald Wheeler's famous quote summarizing the no-hair theorem. A black hole has no hair. Remember, earlier we learned that a black hole completely hides all the unique information of whatever fell into it, reducing the whole shebang to just mass, spin, and charge. Which leads us to one of the most profound, unsolved mysteries in modern physics today. If everything that falls into a black hole has its complex information hidden, and then the black hole slowly evaporates into totally random, featureless Hawking radiation until the black hole is completely, 100% gone, where does all that information go? A fundamental rule of quantum mechanics is that information can never be truly destroyed, yet a black hole seemingly destroys it. This is the black hole information paradox. It basically means that either our understanding of quantum mechanics is wrong, or our understanding of gravity is wrong. And somewhere out there in the dark, the black hole holds the answer. So what do you think?